In this video, I'm going to be talking about what is unit root and how to find out presence of unit root in a time series using unit root test. Alright, so the outline for this session is that we'll first talk about what is stationarity and what is non-stationarity in time series, which is the common thing in time series data. Then I'll talk about what is deterministic and stochastic trend and what the difference between these two types of trends. And then I'll talk about what is random walk, and then I'll talk about the unit root, and then the unit root test, and then I'll finally talk about the Dickey-Fuller test to find out unit root. So that's what we are going to learn in this particular session. Okay, so in time series, stationarity is very common. That means you need stationary data for forecasting. Okay, but many times most of the real world data is non-stationary in nature, and non-stationarity can bring problems, and that has to be very well dealt with. Okay, so you need to make non-stationary series stationary to be able to use that for forecasting. And non-stationarity could come in various ways. It could be non-stationary through by being a non-constant mean. So going, the definition of a stationarity is that you should have a constant mean and a constant variance. So that loosely what we say, that what we mean by stationarity in time series data. So the two important things are mean of the mean of the time series, and the other one is the variance, right? So we are concerned about the mean and variance of the time series when trying to understand whether the series is stationary or not. So the mean could be non-constant. Okay, so all these two have to be constant, and sometimes mean would be non-constant. And here you can see. So mean and variance have to be constant for a time series to be called as a stationary time series. Okay. Sometimes the mean could be non-constant. So the first case of non-stationarity could come from the mean being non-constant. As you can see in the particular time series graph, you can see the mean is not constant in nature. It is increasing, right? It is an increasing trend. So the mean is increasing with time. And that's a typical case of non-stationary time series. Sometimes the non-stationarity could come from uh, by it could be through variance as well. So you could have a non-constant variance, and that could also be the reason for non-stationary. And sometimes there could be both non-constant mean and non-constant variance. So here is a typical example. So the second example is a case where it's a constant mean. You can see the mean is very much constant, but the variance is actually increasing over time, right? So that's a typical case of non-stationarity due to non-constant invariance. Okay. So in this particular session, we will only be concerned about the non-stationarity in mean. Okay, so we are not concerned about non-stationarity in variance, because that's where the focus is for this particular session, and unit root is something that we can relate to a time series data where we have non-stationarity in mean. There are two aspects to non-stationarity in mean. In one case, you will have a deterministic trend, and we'll talk about what deterministic trend is, and the other one is where you have a stochastic trend. Okay, so deterministic, as you understand from the word itself, something that we can easily determine. Okay, so without having to go through more of a uncertainty. Okay, whereas in stochastic trend uh, you have not uncertainty. Okay, so that's more difficult. So deterministic trend is somewhat easier to understand and sort of handle, and stochastic trend on the other hand is somewhat more difficult because it's uncertain. So let's see what deterministic trend is. So a deterministic trend is when we say that the series is trending because it is an explicit function of time. So that's the definition of its deterministic trend. And here's this example, simple to understand. The time series yt is just a function of the time. Okay, so yt is just a function of time and nothing else. Okay, just constant. I mean, alpha is just constant. At is this error term. Sometimes we use at epsilon t. I've just used at at. Okay, and beta is the slope parameter. Okay, so the only variable here in this equation is t. So yt, the time series, is a function of time. So it all depends only on the time. So if you increase the time, the value of the time series will go up. So time is not, t is a certain variable, like a deterministic variable, deterministic or something that is known to us, right? So it's not uncertain, so to say. Okay, so that's the reason why we call this as a deterministic trend. That means that there is a trend, it's an upward trend, and it is very well known to us because we know what time is, and if you know time, you can very well calculate or find out what the value of yt is. All right, so we'll just try to modify this equation or rephrase this equation a certain way. So what we have done here is that, so let's go back, we have space here. So let's say we have yt equal to beta, sorry, okay, I'll go to here. So I'll just take for yt and yt minus 1. Similarly, you have beta t plus at, and then yt minus 1 equal to beta t minus 1 plus at, and then you subtract. Okay, this is equation 1, this is equation 2. So that means this is the time series equation for time t, and this is time series equation for time t minus 1. And if you subtract second from the first, you'll get an interesting pattern. So what do you get? Okay, so basically get beta t plus beta t minus 1, and then at, and at of course will sort of become another 80, maybe this is 80 and this is 80 dash, we'll call it. Okay, so 80 minus 80 dash, this is some sort of error, and the properties will more or less be same. So what is remain with us is that if you take the beta as common, because this is common here, you will see that inside if you take beta, it's t plus t minus 1. Okay, we have made a mistake, so this has to be a negative, right? Okay, so here it will be negative, this is positive. So t and t will cancel, and what we have is just a beta. Okay, that's exactly what we have done here. Okay, so what we have done here is that this is delta t, delta yt, which is the difference between yt minus 1. Okay, and this is nothing but beta, and you have at and at minus 1. Okay, and when you take an expectation of error term, so expectation is nothing but the mean, and mean of the error term, as you know, is just the 0. Okay, because mean is a white noise series, and you just take the mean of the error term is a white noise series, and you take the mean of that, it is always going to be 0. Okay, so that part gets cancelled when you take expectations. So expectation of the change in yt is nothing but your beta, and that's the important thing. So in a deterministic trend, you take the mean value of the change in your time series, you end up getting what is known as the slope coefficients. So in such a case, your slope coefficients is nothing but the difference between the values of the time series for a consecutive time period. Okay, and that's the reason why this type of model is known as trend stationary time series model. Okay, that means it's non-stationary but with trend. So you can, if you handle the trend, you can very well forecast the series without any issue. Okay, so here is this example. I mean, we have just simulated some data for it, and you can see it is increasing over time with slight variation, and this variation is only because of the error term at. Okay, so because of this error term, there is slight variation, and it could start from 0 and it could start at a non-zero value as well. Okay, and we'll talk about it, when it starts with 0 and when it starts with non-zero. But it's always going to be upward, because with time it is going to be increasing, and depending on the sign of the, your beta also, right? Sometimes it could go down also depending on what the sign of beta is. So this is the ACF, and this is the PACF. You can also see there's a clearly there's nothing that we can infer out of it, because there's no point building a model for a non-stationary series. We have to first make it stationary before we can even think of forecasting the series value for future. All right. So deterministic trend could also sometimes come in exponential form. Okay, so it need not be just linear form that we have just seen. It could also be through exponential trend. So you can see here that we have logarithm of the time series, and that's just function of alpha, which is constant, plus beta t, which is a function of t. So instead of yt being the function of t, here we have logarithm of, so logarithm of the time series yt takes care of the exponential trend. Okay, and it's a function of time. Okay, and if you do the same arithmetic that we just did in the few slides back, you'll end up with this particular expressions. So expectations of the difference in the logarithm of yt is nothing but your slope parameter. Okay, so it's just the same. It's just that in exponential trend, the difference in the logarithm of the time series rather than the actual time series value is just the beta. Okay, and it's again something that can be handled very well. So if you just take out this trend from the data, and you can make it stationary, and you can go ahead with forecasting future values. Stochastic trend, and it's different from deterministic trend. So we'll understand how stochastic trend is in fact different from a deterministic trend, and how this can be handled differently than the deterministic trend. So we'll start with an AR type model. So we have yt, which is just equations is like that. We have a constant, and then it's a function of its previous values, yt minus 1, and we have error term. Remember, in deterministic trend we had yt is a function of just the time. Here yt is a function of its past values, yt minus 1. So yt can be found out from the previous value of the same time series. Now the previous value of same time series is not something that is known to us, unlike in the first case, in the deterministic case, where we know for sure what the value of t is going to be, because from time 1 to time 2 to time n, it is very well known to us. Whereas in the case of stochastic trend, it is not well known to us, because the previous price is something that is very stochastic or probabilistic in nature. Depending on what the previous value of the price of the stock, the time series was, it will determine what is going to be the future value of the time series. Okay, and that's why it is called stochastic, because it is so uncertain. Okay, it doesn't quite depend on a certain amount or a deterministic amount like t. It will rather depend on a very uncertain thing or uncertain quantity, which is its previous previous in the case of, let's say, stock price of future depends on stock price of past, and stock price of past is always something that is uncertain, right? Now here is something interesting to know, and we should be very careful here. Okay, so as long as the slope parameters, so in the deterministic case we had this beta, right? Something similar here. Okay, we have used this phi operator. Okay, if phi, the modulus of phi is less than 1, then it is stationary, and we have no issue with that. We can simply go ahead with forecasting the future values, and everything is fine. But there could be cases where the modulus of phi could be the 1, or modulus of phi is greater than 1. Now our topic this particular session will be more concerned about the cases where we have phi equal to 1. So how do we deal with such case? How do we define this, and what exactly is the situation when you have the modulus of phi is 1? Okay, and that's very interesting aspect of a stochastic trend, which is not that straightforward. It's not stationary. It's a non-stationary case, and it's a case that is of interest to many people, because in the real world, many situations are cases where we have the modulus of phi equal to 1. In fact, this is some form of random walk that we'll be talking about, and we'll see in the next few slides, what the forms are. All right, so when phi takes a value of 1, the series becomes yt equal to constant, and then you have yt minus 1. So phi takes a value of 1, so there is no coefficient, and then you have the error term, right? So if you think intuitively, so let's say, example of stock price. Stock price of tomorrow is just the stock price of yesterday plus some constant. Okay, and then you have error term. Right, such a series is very difficult to forecast. This is a typical case of non-stationary series, and we'll talk more about it. Okay. So here is this stochastic trend where the phi takes a value of 1. So the first series is yt equal to c plus yt minus 1 plus at. Similarly, you can write let's say yt minus 1 equal to c plus yt minus 2 plus at minus 1, and you put that in this equation. So in place of yt minus 1, we just put this particular equation, and that's what we have done here. C plus this particular thing I've just taken from here, and then you have the error term. Okay, and you keep doing that. For yt minus 2, you can also write that in terms of yt minus 3, and you keep doing that, and ultimately you will reach a point where you will have y0. Okay, and you have t times the constant, and you have summation of the error terms, which eventually gets to 0 when you take the expectations. Okay, so the idea here is to understand is that in a stochastic trend, there is some kind of uncertainty, and the problem arises when phi is 1. It takes a value of 1. When it's less than 1, the series will converge. Okay, and when it's not less than 1, it is either 1 or greater than 1, the series will less likely to converge, or it's probably not converge, and that's a case of typical non-stationarity. Okay, so just to deviate from what we are talking, so why do we really want phi to be less than 1 for stationarity and so on? So what happens when phi is less than 1 is that when you plot the time series, it is going to be mean reverting. That means the time series will come back towards mean every time it goes up. If it goes up, it will certainly come towards here, and then it goes up and comes towards. So it will be somewhere near that mean. Okay, so the mean will be constant, and moreover the variance will also likely to be very constant or near constant. Okay, so that's one of the property of phi being minus 1 here. Okay, you can actually mathematically prove that the series is converging if phi takes a value of less than 1. Otherwise it is not going to converge. All right, so this is a typical case of a random walk model. Okay, so yt equal to yt minus 1 plus the error term at. So this particular thing is a typical case of random walk. Okay, and if we include the constant part, then it is drift. Okay, that means the series has started not just from zero origin, it started somewhere here or somewhere here, some negative or positive value. So if you have a if I have a drift, we call that as a drift. If c takes a value of 0, it's called random walk. Okay, so random walk is nothing but yt equal to yt minus 1 plus at. That means the next future value is just the past value plus some error term. Okay, and that's very difficult to even predict. We'll see that by simulating a series. So we'll take these two trains, deterministic and stochastic train, and visualize it using ARCH. So we'll simulate data. So how do we do that for deterministic train? All right, so what we'll do is that we'll use the ARIMA procedure, and ARIMA.sim will give you data, simulated data from the ARIMA model. Okay, and we'll take an AR1 process. Okay, because your deterministic trend is more of an AR1 type, where you have it's not AR1 type. It's just that we are trying to find out some AR1 terms which we will be adding to make sure that we have a deterministic trend. So you just simulate an AR1 series, which ideally should have a mean equal to 0 and variance of constant variance and so on. Okay, all right. So constant mean and constant variance is the idea here, because and mostly 0 mean. So once we have that, we will create a series called y equal to 2 plus and this time function will give you the time point of each data points in this particular series. So if you run this on your own, what you will find is that x will have many values like 0.2, 0.4, minus 2. So these are the time series data with more or less mean 0 and variance constant. And then when you take the time function of that, you will get for what time period you have this data point. Okay, so time period 1, time period 2, and so on. Okay, so we have so y is a function of time, right? That's what deterministic trend is. And then we are just multiplying with 2, and then we are adding a random term. So x, basically the simulated series will basically have random terms, and you just add them to this deterministic part. You have this drift 2 plus time, that means let for its time equal to 1, then 1 into 2. If time equal to 2, so it's 1 into it's 1 into 1, and if time equal to 3, this is 1 into 3, and every time you just keep adding some error term. If you do that and plot it, you find this type of a graph. You can see it's an upward trend, and this slightly varying, because upward trend is because only time is increasing, the value of yt is increasing, or the value of time series is increasing, and the variation around this trend is because of the error term. Okay, we'll do the same thing for stochastic trend as well. Okay, however, in stochastic trend we will use you will use an ARIMA 0, 1, 1. If you're familiar with ARIMA modeling, so 1 stands for the integrated, okay, and this is the MA term, so it will be MA1 and I1 series. Okay, so both combines, you just ARIMA 0, 1, 1 series. Okay, so in that case, we know for sure that if you difference once, and then you will get a stationary series. That's why we have taken stochastic trend, and we know that. So people who do not know what differentiating is, just ignore that part. But just for simulation purpose, I have taken an ARIMA 0, 1, 1 series, and you will get this data. Okay, and we don't have to create any y terms. Directly we can actually plot x to find out how it looks. Okay, if you actually plot it, you will get something like this, and you see this series is clearly non-stationary. You can see the mean is changing every time, right? The mean is changing every time. The variance is also, there's nothing can be said about the variance. Sometimes it is pretty high, this big, sometimes it is much smaller, right? So it's clearly a non-stationary case. You can also look at the ACF and PAC value, although that's of no use unless, of course, you want to make it stationary before forecasting. All right. Now we'll talk about the random walk process. Okay. Now we are interested in the stochastic trend, and one of the special case of stochastic trend is random walk process. And when is that going to happen? When the psi takes a value of 1. Okay. So how do we define? A random walk is defined as a process where the current value of the variable is composed of the past value plus an error term. Okay. So there are two important things in a random walk series. You have the past value term and the error term, nothing more than that. So yt is the current value, it's just the past value plus an error term at. Okay. So this is typically also known as white noise. Okay. Where you have zero mean and variance of 1. Okay, so in such a case you will not be able to use time series. Okay, for white noise there's no point using time series. There's nothing can be done for time, in a white noise series. Okay, so just avoid using anything for such process. So how do we let's say, and what's the motivation behind understanding random walk process? Well, when you have a time series data and you find out that it's following a random walk process, then you stop there. Okay, so that's basically a check that one needs to do before even going for other forecasting, using other forecasting techniques. Okay, so if you plot a random walk process, it looks something like this. Okay, it looks very weird. There's no trend at all, there's no pattern. So basically what random walk means is that there is no pattern in the data. There is no pattern in the data, just pure random. Okay, and there's nothing in the data that you can use for forecasting your future. Something similar. Okay, so this is also a typical random walk process. Okay. Okay, so random walk process can be closely related to the behavior of stock market. Stock market also many times doesn't have much of information in the past values. Although many people will say that forecasting stock price or return is very much possible, but that's not always the thing. Stock market many times behaves purely as a random walk. Sometimes it has some pattern, but many times it has no pattern in it. It's also used in understanding Brownian motion in many science and science areas, also in finance. A movement of a drunken man, somebody who's drunk, you will have no pattern. If you try to understand or study his pattern of walking, there's no pattern at all. Okay, so it's also a limiting process of an AR1 process. So AR1 process is just yt equal to yt equal to phi y minus t plus at, right? So this is an AR1 process. So when phi equal to 1, you take a random walk process. Okay, if phi is less than 1, you have the AR1. Okay, so this is a typical condition for AR1. So random walk is basically the special case of AR1 where you cannot go ahead in building a forecasting model. So what the implication? What is the understanding or the takeaway point? The takeaway point here is that the implication of a process of this type is that the best prediction of y for next period is the current value. Okay. Now, if you have a time series data and that follows random walk, just stop there. Don't have to do anything. So you all need to convey, you need to communicate to the audience is that the best prediction for this particular time series for future is nothing but the current value. There's nothing more can be done other than that. Okay, it can be shown that the mean of a random walk process is constant, but the variance is not. Okay, so mean of the random walk in many situations it can be constant, but variance is never the case, and that's why random walk is a typical case of a non-stationary series. But many non-stationary series can be made stationary, and you can do forecasting for future, except in the random walk process. That's where the difficulty is. Okay, sometimes you could have a deterministic component to random walk also, and we call that again as a drift. Okay, you have a constant term to it. Okay, so instead of just yt equal to yt minus 1 plus the error term, you could also have something like theta. Okay, theta naught. Theta is just the drift. Okay, so this is the deterministic term, and this is the stochastic term. Okay, so it will be partially deterministic and partially stochastic in this case. So it doesn't start from 0, right? It starts somewhere here. So that's the drift. So this is the theta naught, and then there is no trend at all. Okay, so it has some deterministic part and some stochastic part. Okay, so this is the typical case of random walk with the drift. So how do you remove the trend, okay, from a series? A series containing a trend will not revert to long run mean. Okay, so if a series has some kind of a trend, it is either upward trend or there is a lower trend, it is never going to, let's say, come back to the mean. Okay, so this series something that you can't expect, but that's what is needed for forecasting, right? So the usual methods for eliminating trend is detrending and differentiating. Okay, either you detrend or you difference. I'll briefly talk about it, not in detail. So here is the case of differentiating and how you make something stationary. So okay, so if you take a random walk, okay, so a random walk is yt minus 1 equal to your error terms. Okay, sorry, this is wrong. Yt equal to yt minus 1 plus your thing, right? So this is a typical case of random walk. Here at will be non-stationary. So in this case, this is a typical non-stationary case. But if you take a difference of that, it is likely to be stationary. If you take the first difference, it is likely to be stationary. So this is where we need to understand what is known as an unit root test. So the name suggests unit root means we are only talking about how to find out whether the phi that we talked about in the non-stationary series is 1 or not. Okay, so in a stochastic trend series that we have just learned, if phi is 1, then we are sure it's the random walk process, and that's what we call it unit root, and we need to statistically test that before getting to know. So when we have a stationary system, we know for sure that the effect of any shock that is going to happen to the time series will die out gradually. Okay, in a stationary series, if you have a shock, it moves up, it eventually comes down, and then it removes somewhere in the mean, and then even if there is a shock in upward or whether it's downward, if there is downward shock here, it will again come back. But that's not the case in non-stationary system. In non-stationary system, if there is a shock, okay, if something goes up, it never comes down to the mean. Okay, so it never approach the long run mean. Okay, so that's one aspect of a non-stationary series, and from there we can derive some sort of a clue as to how we can find out if there is presence of unit root. That means whether the phi is 1 or not. All right, so there are two types of non-stationary. Okay, one case where you have the this case is just 1, and the other case is phi is greater than 1. Here we just taken beta, just keep changing notations, but the second case we of course will ignore for here. So the first case we would like to see when is the case when we have the phi equal to 1, and that we can get to know using Dickey-Fuller test. Okay, so this is a test using which we can find out whether there is presence of unit root or the time series is unit root or not. So unit root is just another way of saying that whether it's a random walk series or not. All right. So the simplest approach is just to have a AR1 series, okay, yt with the theta, and you have psi of yt minus 1, okay, and we would like to know if psi if phi is 1 or not. Now this is AR1 series, right? And we expect phi to be less than 1. If it is equal to 1, then that's a problem. That's a random walk series, right? So the hypothesis testing in the case of a Dickey-Fuller test is like this. The modulus of phi is either 1 or modulus of phi is less than 1, which is the alternative hypothesis. Either this will get accepted, or we'll just reject null hypothesis, right? Depending on what the test statistic value is. We can rephrase this to make it better, right? Because in a t-test we essentially compare it with the 0 or non-zero, right? So we'll make it more simpler. So how you do that? You just subtract the previous time series from it. Okay, so we have yt equal to yt is theta theta 1, let's say, minus phi 1 yt minus 1. Sorry, I think we have done something else. Okay, so we have the series yt equal to yt minus 1. This is theta naught plus at, and then what we do is that we simply subtract yt minus 1. So from left and both right, yt minus 1 equal to theta naught, phi, this is theta, theta naught plus yt minus 1, which is again phi here, minus yt minus 1 plus at. Okay, now this is just delta t, right? So delta yt is equal to theta naught plus, here we can take yt out, so yt, then inside we have 1 minus phi plus at, and then 1 minus phi we just denote with some other symbol. Okay, so so this particular term, if it is equal to 0, then we have a unit root, otherwise not. So it has now changed. Okay, so null hypothesis is now either it's 0 or it's less than 0. Okay, so just slight change. Here we are comparing with 1 or less than 1. Here it is either it's 0 or less than 0. There are 3 types of Dickey-Fuller test we can do. I'm not going to the details of it, but depending on the kind of random walk we are trying to understand, we'll have different type of Dickey-Fuller test. The first case is a pure random walk. There is no drift. There is no theta term here, right? It's just the past value of yt. Okay, so we would like to know if the coefficient is 0 or not in this case. The second case we have a drift. Okay, and in the third case we have a drift, and we also have a deterministic time component. Okay, we have theta 1 t, so time, right, it's the deterministic trend, so it's just a combination of deterministic and stochastic trend. Okay, linear time trend. Okay, so there are 3 types of Dickey-Fuller test we can do depending on what type of what the intention is. I mean, we can also do all 3 and see which one is actually is the best for the given time series data. So how do you find a test statistic, and how do you do that? Right? You just apply Euler's, you have the equation, regression equation. You just find we just estimate the parameters. So parameters here is phi, right? Remember it's 1 minus phi. We just change it to different symbol, but ultimately we are trying to find out what phi is. So we can find that out using Euler's. And then we can find out the t statistics. Okay, we can find out the t statistics, and then we see whether it's significant or not given for a given particular value. Okay, so that's how you will get to know if a particular time series is a unit root case or not. And if that is the case, you will be able to find out whether it's a typical random walk or not. In such a case, the limitations of time series methods won't allow you to, let's say, forecast future. You would rather take more of a guess depending on the past values of the time series, rather than doing some sort of analysis that is not going to give any accurate result. So that's one of the important tests that people do before even starting to explore other time series models for forecasting. And it's quite important early enough. If you get to know if a particular time series is random walk, then you do not go ahead with any of this sophisticated methods. You will be saving a lot of time in doing that. Hi. So in this video, we'll learn about the ARCH and GARCH model. It has few components. It has a big background of what is volatility modeling and how is it different from the normal forecasting model like ARIMA model, and what is the purpose of building a volatility model. So the idea behind volatility model is that the error term that we know in a time series is serially uncorrelated but dependent. That's important to understand here. They're uncorrelated with each other, that's an assumption, but they're dependent in some way. So one model to describe such dependence was given by Eagle, for which he received a Nobel Prize, and that's when the ARCH model came into picture. Now, heteroscedasticity is the problem that you often come across in cases where you have time series data, and to model that we use the ARCH model. So we'll see that here. So here is a typical example of heteroscedastic data. Okay, so E is error term, and HT is defined like this, just a summation of the previous lags, and VT is another white noise process. Okay. Now there are a few things that we need to remember here. See, the idea before the volatility modeling is that we want to know the volatility of the error term. So that's the idea here, the volatility of the error term. What happens in time series is that sometimes you will have higher volatility. Okay, higher volatility. Stock returns could be higher volatility, then it could be lower volatility, then it could be again higher volatility. So because this volatility is nothing but the standard deviation, the variation is often uncertain, modeling for volatility is important. So that's the idea here. So how do we model? So there are two ways to model. One is ARCH, the other one is GARCH. ARCH is the autoregressive conditional heteroscedasticity. GARCH is the generalized autoregressive conditional heteroscedasticity. This is more of a generalized form of ARCH. Essentially both are similar. A simple GARCH model, by the way, ARCH is just a one spatial scenario or spatial situation of GARCH model. So a GARCH PQ model can be written in this form. We have this error term in this case, and we have got this formula for GARCH representation. So you model volatility. You will model volatility of so volatility is nothing but variance. Okay, variance of your error term. So you model that using the volatility of your previous error terms and the summation of h square that we have seen last time around. So that's the idea here. and the parameters are nothing but the AI and BI, and that's the parameter we need to estimate from the GARCH model. So here are the steps. So how do you fit a ARCH model to stock return in R Studio? So first you load the data, calculate return, and we'll see why calculate return, why not stock price. Check the return series for stationarity, fit an ARIMA model, and look for evidences for need of modeling volatility. If there is no need for volatility modeling, then there is no reason to model it. But if at all there is a need, then you need to. Otherwise, ARIMA will do the job. Fit an appropriate ARCH and GARCH model. Then how do you get to this? Just get the data from Quandl. Quandl is a very good source of getting financial data. You can get the data directly onto your R by just calling, calling a Quandl package. So you get your data using this R command, and before that you have to install Quandl package in R. Return. So why do we go ahead with return instead of um, stock price? Well, return provides scale-free summary, right? The return is scale-free, whereas stock price could be in dollars, in rupees, in pounds, anything, right? And the statistical property of return series also is better than the stock price. Then some theory about single period return, multi-period return. If you're familiar with financial mathematics, this is just easy, right? Simple return could be just price of today's data minus price of yesterday's data by price of yesterday's data. So this is exactly what we have written in just another form. However, we do not use return, we use log return for many reasons. Okay, and the primary reason why it is being used, because log return follows normal distribution. Okay, a return series doesn't follow normal distribution, it follows more it's not normal. So we need normal distribution of a series, hence log return is preferred. So stock prices are usually distributed log normally, hence log normality is okay. The single period return, multi-period return, just do away with the mathematics. It's not required though, because most of the times we'll work with a single period return. So that's enough, to learn what the ARCH and GARCH modeling is. You can calculate both single period and multi-period return using R. So first step is checking stationarity. If you're familiar with the ARIMA model, you must be knowing what is stationarity and how do you ensure that the model is stationary or the series is stationary. There is strict stationarity, weak stationarity conditions. Joint distribution should be similar, so that's your strict stationarity. And then you have weak stationarity. That means these criteria should be filled up, and you can check by using statistical test. Just do an ACF, ADF test, and you'll get to know stationarity of the series or not. And then you also find out what are the AR and MA terms using ACF and PACF term. So here is the plot of the log return. You can see this sort of a clustering, right? This is more of a cluster data. Hence, we'll see that that's useful. It's not, but the rest of the series is very normal. So this is the data for Ranbaxy. This is a pharmaceutical company in India, and we have taken the return series for a specific period for Ranbaxy. Here is the ACF and PACF. So the ACF and PACF shows that they are both declining in nature, and they seem to be stationary. Although you should go ahead with hypothesis testing, but even at looking at the ACF, PACF, it is very sure that it's more of a stationary series. Yeah, you can also do augmented Dickey-Fuller test. I'm not going to get into the details because we have covered that in ARIMA. It's easy to do, and just do it just to know how many
differentiating you should do, how many integrated terms you have to be there in the you have to have in the ARIMA model. So here is the result from the augmented decoupleur test, and what we have received from the R package is that the value of test statistic is minus 23.8677, which is smaller than the critical values at 1%, 5%, and 10% level of significance. Hence, we reject the null hypothesis of stationarity, conclude that log return series is stationary. So, non-stationarity is not an issue here. So we don't have to integrate it. We do not have to integrate this one because it's already stationary. Otherwise, you would have to. So fit an appropriate model. Just fit PQR, which is AR integrated and MN terms, and see which ARIMA model is actually fitting. So when you do that, all right. So we just sort of just look at the ACF, PACF, but don't take them very seriously. You can always try new terms in AR and MA and see what is the ACF and PACF term says, what is the AR and MA. You can always get to know, right? From ARIMA model, you might have learned how to pick the AR and MA terms. So we just tried out ARIMA 201. You can also try out 202 and so on, and see which one is your best model. Okay. So you found some sort of a return series with ARIMA. Will that work, or do you also need to volatility? Okay. So ARIMA will give you the mean of the series, whereas volatility modeling will give you the variance and the standard deviation, right? And the standard deviation. So we need both. If the mean varies with respect to the series, then we need the standard deviation of the mean. Okay, so that's exactly is known as the volatility modeling. So we'll understand what is volatility clusters. So this is nothing but periods of tranquility and turbulence clustered together that could happen in stock market. This can be observed from the plots in the residuals squared obtained from the fitted ARIMA model. You can see the square of the residuals. You can see that there is sharp rise and then sharp fall. And this happens with stocks. It goes up suddenly, it goes down again suddenly. So that turbulence in the stock market could cause this. And when you square this, you will have a better visualization. When you square it, right, your negative terms are always going to be positive because you have squared it. So you can see the number has actually, it's more evident here. The visualization is better when you actually square it and plot it. Series is leptocortotic. Okay, so leptocortotic is nothing but deviance from normality. Okay, so if a graph is cortotic, it is not normally distributed. That's essentially is the term. If something is not normally distributed, it is cortotic. Okay, either left or right. So you do a QQ plot, and you get to know whether there is. So QQ plot is nothing but normally if you have a normal distribution, this line, right, this data points will lie on this line. If they are very deviating, then there has to be some sort of a cortotic. Okay, and we have concluded that it is cortotic. Hence, there is a need of volatility modeling. Remember why it is volatility modeling is needed? Volatility modeling is needed. So that means from the last two plots we have seen that we see a lot of deviation from the normality. So we should go in for a volatility modeling. The last one is dependence. So from ACF and PACF, one can infer some sort of a dependence. Okay, the plots show some significant correlation. However, there is no evidence of serial autocorrelation. So you see there is some correlation here. There is some high correlation here. There is no autocorrelation for for that matter. I mean, there is no serial autocorrelation. I mean, there is no continuous as such. It's just one of time, right? which means there is a dependence of square residual on its past realized dependency. So these are evidences to tell you that volatility modeling is needed. So visual inspection we have done. We have done using graph. We have seen 3 graphs to showcase that volatility modeling is required. We'll do a statistical test here. We'll do the Chong box test. It's used in other areas also. It's also used here as well. The null hypothesis is that no autocorrelation arch effect do not exist. Alternative is arch effect does exist. So you just use this code SAS syntax to do the Chong box test. Look at the p-values. It is greater than 0.17. So which one will you accept? You'll accept the null hypothesis, right? Arch effect does do not exist. Is it so? No. The value of test statistic is 0.1, okay, which is smaller than the critical value. Is it smaller than the critical value? Okay. Hence, we reject the null hypothesis and no correlations. Okay. So the idea here is that, see, we have been little conservative, so we have taken it as a 90% confidence. Okay. And at 90% confidence, it is, this comes out to be significant. If you take 95, okay, I think you have taken 95. Sorry, we have been more conservative. 85. Even at a 95, this is not significant because 95 it has to be p-value has to be sort of less than 0.1. Okay, that's not the case here. But we have taken it as 85%. So we have been a bit conservative. The idea is to show you the arch effect. Okay, otherwise in a real scenario, of course, you will reject this. But getting a real scenario is difficult. So just assume that let's, for sake of illustration, let's take this as 85% and just proceed with this. So we assume here that there exists arch effect in this case. So fitting an appropriate arch model, how do we do that? We'll now proceed to model the conditional volatility as an AR process to allow predictability of conditional variance, such as autoregressive conditional heteroscedastic model, or in short known as ARCH Q model. It has got one parameter, only Q. Okay. So ARCH model is just a subset of GARCH model. Okay. ARCH and GARCH are basically same, except the fact that GARCH has 2 terms, ARCH has 1 term. So when you put the second term 0 in GARCH, that means in ARCH. So here we use GARCH fit, and we are, you see the right hand side is always 0. That means it is a ARCH model. So because ARCH model has only one parameter. So there is 1 lakh, 2 lakh, 3 lakh, up to 10 lakhs. We just tried it out. How do you select which one is the best? Look at the AIC value. The minimum one is the best one. Okay. And look at the output. Which one is giving you the minimum? Okay. So here is the AIC values for respective, what do you call it, models, and see which one is giving you the least one. So we have found out the ARCH 7 is giving you the least one. So your model, ARCH model, is like this. So you can find the volatility using this particular expression. There are 6 terms, I guess, right? 7, right? Yeah, 7, because I ARCH 7. So there are 7 lakhs here, and we have found it out. That's ARCH model. How do we fit a GARCH model? GARCH is nothing but a generalized ARCH, but it's more generalized form of ARCH model. So we have 2 terms here, not just 1 terms. Okay. So we have 2 terms, right? 1 0, 1 1, 1 2, and so there are multiple. There are 2 terms, but the syntax remains same. So we fit all the possible GARCH cases, and we have found out the AIC. Again, the criteria to choose the best model is AIC, archaic information criteria. You always get that in your output. And we have found out that GARCH 4.3 has a minimum AIC, and that's exactly what we use for finalizing the last model. So this is the final GARCH model. Okay, it has got the error terms as well as some of the alpha terms, and alpha is defined in the beginning part, right? So Yeah, so that's the GARCH model, which is different from the ARCH one. So the AR and ARMA, they're also a bit similar, right? Similarly, ARCH and GARCH are also a bit similar. Just that ARCH is just a special scenario of GARCH model. Now you should be able to answer some of these questions that are posed at you. These are some of the questions that you would be wondering about the ARCH and GARCH model. Thank you.